Welcome back, guys. If you've made it this far, you are now halfway through the course. So let's move into our next chapter, which is rigid and flexible pavement structural design using the ASSHTO 1993. So let's start with flexible pavement. So empirical equations, we know that they're used to relate observed and measurable phenomena with outcomes, right? So the phenomena would be the pavement characteristics, the outcomes being the pavement performance, right? So this section, you just presents the 1993 ASSHTO guides, basic design equations for flexible pavements, right? So this empirical equation is widely used and has the following form. So as you can see, that's the equation. And I'm just going to break down what all the variables are, what they mean. So let's get into that. The variables for the equation, you can see what the W18 means. So the W18 is the predicted number of 80 kilometers. So that's your axle 80s. The ZR is the standard normal deviation. The S underscore O is the standard error of the traffic prediction and the performance prediction. The SN is the structural number. Okay. SN is the structural number. I'll explain what the structural number is, but it's an index that's indicative of the total pavement thickness required. So it's like, but I'll explain further as we go in. So those are all the equations. So that's just up until the ith layer coefficient D is equals to the ith layer thickness and the ith layer drainage coefficient. And then the PSI, that's the difference between the initial design serviceability index and the design terminal serviceability index. So that's the difference between where you started and when it's going to fail, like when the road is no longer serviceable, it will no longer be used. Then MR is the subgrade resilient modulus in PSI. Okay. So the equation that I just showed you guys before, like that equation, is not only an empirical is not the only it's not the only like available equation, right? But it does give a good sense of what an empirical equation looks like, right? The factors it considers and how empirical observations are incorporated into the empirical equation, right? The rest of this section will discuss, the specific assumptions, inputs, and outputs associated with the design guidelines, right? And the empirical equation. So the following subset will discuss the assumptions, the inputs, and the outputs you're supposed to get when you're designing empirically using the ASSHTO 1993. Okay, so this is the heart. This is the meat, the fleshy part of how to design using the ASSHTO 1993. So without any further ado, let's jump into it. See you on the next slide. Okay, so the assumptions. So from the ASSHTO road test equations that were developed, which relate to the loss in serviceability, traffic, and pavement thickness, right? Because they were developed from specific conditions of the ASSHTO road test, these equations have some significant limitations, of course. So the equations were developed based on specific pavement materials and roadbed soil present at the test site. The equations were developed based on the environment at the test site. The equations were also based on the accelerated 2-year testing period, because so they didn't go through the whole design life, so the test were accelerated, so obviously that presents room for some error. So the loads used to develop the equations were operating vehicles with identical axle loads and configurations as opposed to mixed traffic, so they only had one vehicle operating, they didn't have various traffic, so also that's a misstep on their part, but obviously they did the best they could, right? So in order to apply the equations developed as a result of the ASSHTO road tests, some basic assumptions need to be done, of course. So these are the assumptions. So even when you're writing your report, you mention your assumptions, right? So these are the assumptions that you have to be mentioning. So the characterization of the subgrade support may be extended to other subgrade soils by an abstract soil support scale. The load can be applied to the mixed traffic load by the ESAL. Material characterization may be applied to other surfaces, bases, and subbases by assigning the appropriate layer coefficients. The accelerated testing done by the ASSHTO tests, the 2-year period, can be extended to a longer design period. These are the assumptions you're doing, or these are the assumptions you are using when you are carrying out the design. Okay, so let's move on. When using the 1993 ASSHTO guide empirical equations or any other empirical equation, it is extremely important to know the equations, limitations, and the basic assumptions, of course. Otherwise, it's quite easy to use an equation with conditions and materials for which it's never intended for. So you need to understand what you're doing. This can lead to invalid results and at the least an incorrect result at the worst. So you can have a totally wrong design. So you need to be very careful. Like I was saying, when you're doing things like this, it's always good to have a senior who's helping you, or a senior that's going to go through your work and make sure that you're doing it correctly. So now we'll move on to inputs. Okay. So for the ASSHTO guide, the equation requires a number of inputs related to load, pavement structure, subgrade support, and these inputs are the predictive loading. The predictive loading is simply the predictive number of ATs. So the ESALs, you can calculate that, and the pavement rules is over a period of time. You can calculate that. You guys should know how to calculate that from varsity. You should know. It's part of the course. It's part of every civil engineering course, so that shouldn't be an issue. Reliability. Okay, so the reliability of the pavement design performance process is the probability that the pavement section designed using the process will perform satisfactorily over the traffic and environmental conditions for the design period. Right? In other words, there must be some assurance that the pavement will perform intended, given the variability in such things as construction, environment. So it's just, you should, even if it's not constructed correctly or it has not been constructed exactly to specification, there's just, and we need a reliability to say, okay, it wasn't constructed, it will perform maybe within plus or minus 5% of how it's supposed to perform. So that's like the reliability in terms of construction and environment. So post-construction, so that's 4.0 to 5% depending upon the construction quality, smoothness, end of life, called terminal serviceability. That's 1.5 to 3 points depending upon the road usage, interstate highway. So all the parameters, how it was constructed, the quality of construction, how it was end of life, the terminal, where do you want to stop its life? Is it going to last for 15 years? It's going to last for 20 years? It's going to last for 30 years? So, and also depending on the road uses, is it an interstate highway? Is it just an urban arterial road? Is it just a residential road? So all of that factors in. Okay. And obviously subgrade support. So subgrade support is characterized by the subgrade resilience modulus, and intuitively the amount of structural support offered by the subgrade should be larger than should be a larger factor in determining the required pavement structure, of course. So if your subgrade is very weak, you'd need thicker layers as you go up so that they can take up the load, and when it gets to the subgrade is not burdened with a lot of load. So that would be the idea there. So you most definitely need to know your subgrade parameters. Okay, so now we'll move on to the outputs. Okay, so the 1993 ASSHTO guide equations can be solved for any one of the variables as long as all the other variables are supplied. So you can just make whatever variable you're looking for the subject of the formula, then you can find that variable. So typically the output is either the total ESAL or the required structural number or the associated pavement layer depth. To be most accurate, the flexible pavement equation described in this chapter should be solved simultaneously with the flexible pavement ESAL equation. This solution method is an iterative process that solves for the ESAL in both equations by varying the structural number, of course. It is iterative because the structural number has two key influences. The first influence of the structural number is to determine the total number of ESLs that a particular pavement can support. This is evident in the flexible pavement design equation presented in this section, so the equation that I showed you guys. The structural number also determines what the 80 kilonewtons, I'll call them the E80. So the E80 ESAL is for a given load. So yeah, so that the 80 ESL, I usually just shorten it and call it the E80. My lecturer also used to call it the E80, so I just prefer calling. So going forward, I'll just be calling it the E80. So don't get lost when I call it the E80. It's the 80 kilonewton EASL. Okay. From everything that I just said previously, we can therefore establish that the structural number is required to determine the number of ESALs to design for before the pavement is ever designed. The iterative design process usually proceeds as follows. Okay, so these are the design steps. I need you guys to pay attention. You determine and gather the flexible pavement design inputs. So you determine your ZR, your SO, your change in PSI, and your MR. Determine and gather the flexible pavement ESL equation inputs, so your LX, your LX2, and your G. Assume the structural number. Determine the equivalency factor for each load type and solve the ESL equation using the assumed SN for each load. Estimate the traffic count for each load type and for the entire design life of the pavement, and multiply it by the calculated ESL to obtain the total number of ESLs expected over the design life of the pavement. Insert the assumed SN into the design equation and calculate the total number of ESALs that the pavement will support over the design life. Compare the ESL values in 5 and 6. If they are reasonably close, say within 5%, you use the assumed SN. If they are not reasonably close, assume a different SN and go back to step 4. So it's just an iterative process. So you can set up an Excel spreadsheet where when you put in, you compare. So, and you can even automate it to say that if they're not within 5% of each other, it says not okay, change SN. Then when you change, when it's okay, it says SN okay within plus or minus 5%, and then you move on. That's very simple to do. You can just Google that. You can just check that on YouTube. There are a bunch of guys that show you how to automate your spreadsheet. So you'd want to put this calculation in a spreadsheet. I have my own spreadsheet. If you guys think you'd be interested in that, just drop a comment and let me know so that I can show you guys how I program my spreadsheet to do all those fancy things. Okay, so in practice, the flexible pavement design equation is usually solved independently of the ESAL equation by using an ESAL value that is assumed independent of the structural number. Although this assumption is not true, the pavement structural depths calculated using it are reasonably accurate. So this design process is usually as follows. So let's go through the design process. So you first assume a structural number SN for the ESAL calculations. Although often not overtly stated, a structural number must be assumed in order to calculate the ESAL, or you just need to assume a number and then you move on. Then you determine the load frequency factor, the LEF, for each load type by solving the ESLA equation using the assumed SN for each load type. Typically, a standard set of load types is used, e.g. like a single unit truck or a tractor trailer or a bus, depending on exactly what the road level service is. Then you estimate the traffic count for each load type for the entire design life of the road and multiply it by the calculated LEF to obtain the total number of ESALs expected over the design life of the pavement. Then you determine and gather the flexible pavement design inputs. Then you solve the design equation for SN. Then you check if your computed SN value is reasonably close to the assumed ESLA calculation. But yeah, that step is often neglected, so you need to remember that. Then what design utility do we get from this? So the design utility solves the 1993 ASSHTO guideline basic design equations for flexible pavement. It also supplies some basic information on variable descriptions, typical values, equations, and precautions. So that is the utility in using this design method. So now let us move on to our second type of pavement. Okay, so now we will look at rigid pavement and how rigid pavement can be designed using the ASSHTO 1993 guide. So as you can see there, we have an equation. So there's our equation that we use. And yeah, the variables, I'll explain them in the next slide. So these are the variables. As you can see, some of them differ from the elastic module. So like here, you've got the slab depth, you've got the terminal serviceability index, the PSI is still the same. Here you've got the modulus of rupture for Portland cement concrete. That's a fracture strength, but you still have your drainage coefficient. You also have the load transfer coefficient at the joints. So the value depends on the load transfer efficiency. So, and you also have the elastic modulus for the concrete, and you also have your subgrade reaction. So those are the different variables from the flexible. pavement. All the rest are the same. So let's move on. So this equation is not the only empirical, obviously we talked about that, and we'll look at the assumptions, inputs, and output. So what are the assumptions? Okay, so for our assumptions here, we will look at the equations were developed based on specific pavement material, roadbed, and soil tests. So the assumptions are more or less the same, except for this one. Okay, so for JPC and JRCP. So JPCP, that is joint plain concrete pavement, and JRCP is joint reinforced concrete pavement. So yeah, apologies for not, like because I use these terms, I know them a lot, but maybe you guys might not be familiar with it. So those are what those abbreviations means, right? All transverse joints were the same spacing, so that is 4.6 meters and 12.2 meters, 4.6 being 15 feet and 12.2 being 40 feet, right? All transverse joints used door bars, and all plain all Portland concrete cement was of the same mixed design and used by the same aggregates and same Portland cement. So the assumption was they use the same mixed design and they use the same type of concrete, whether it be a Sim 1, Sim 2, whichever, doesn't really matter, but they're just saying that everything in this experiment was exactly the same. Okay, so let's move on. So, like, in order to apply the equations developed as a result of the ASSHTO road test, the basic assumptions. So the assumptions are exactly the same as the assumptions for the flexible pavement, so I won't get into that. So yeah, and so while using the 1933 ASSHTO guides empirical equations for any other empirical equation, it is extremely important to know the equation limitations. We talked about that. You need to know the limitations so that you don't make a mistake, or you know that you're using the correct method. So yeah, that speaks for itself. So let's move on. So here now we're moving on to the inputs. So obviously the inputs are different. So the inputs we require here, the predictive loading. So we require our E80s, right? That's the same. We also require our reliability. We talked about that. And then obviously we require the PCC elastic modulus, okay? So if there's no value for the PCC elastic modulus can be estimated. So this is the equation to estimate the value where E underscore C is the PPC elastic modulus, and our FC is equal to our PPC compressive strength. Okay. So, if no compressive strength data is available and you cannot assume, you assume EC to be that, and you assume EC to be that, which is that in PSI, which is 4 million in PSI. EC is 27,500 MPa, right? Which corresponds to a compressive strength of 34.5, right? That's the compressive strength, which is about 35 MPa, which is the compressive strength. So that's the compressive strength you would be designing for your concrete. But in this case, I'll just then go to 40 MPa because, that extra 5 MPa is a buffer, and I'll feel safer. It might be a bit of an over design. It will cost more, but, it reduces your risk as an engineer, and you'll sleep better at night. Okay, so the PCC modulus of rupture, right? So this is the modulus of rupture. That's the SC is typically obtained from flexural strength test. The slab depth, the pavement structure is best characterized by the slab depth. That's D from the parameters. The number of ESALs, right, of a rigid pavement carried over time. It's a very sensitive slab depth. A general rule: beyond about 200 mils, the load carrying capacity of the rigid pavement doubles for each 25 mils that you put in. But yeah, so that's something that's just a typical design practice where after 200 mils, if you just increase 25 mils, the rigid the carrying capacity typically doubles. Okay. Then obviously there's the drainage coefficient. So rigid pavement is assigned a drainage coefficient that represents the relative loss of strength due to drainage when water seeps in. Okay. So generally, quick draining layers that almost never become saturated can have a coefficient as high as 1.2, while slow draining layers that are often saturated can have a drainage coefficient as low as 0.8. If the subsurface drainage is expected to be a problem, positive drainage measures should be taken, right? So in general, the use of the drainage coefficient to overcome poor drainage coefficient is not recommended, right? More slab, like making the slab thicker, does not solve water-related problems. That's just an FYI. Because of the peril associated with its use, oftentimes the drainage coefficient is neglected and you just set it as 1, which is what I typically do. Kind of, that's what I'd advise, but you can just consult your supervisor and see what he thinks. So the serviceable life, so the difference in present serviceability, like your PSI, right, between construction and the end of life serviceability, so the equation comprises this default value of 4.2 and immediately after construction the value of 1.5 after, right? And it's also good to note the typical values used now. For post-construction, you can use 4.0 to 5 depending on the construction quality. Of course, you'll see as the engineer, you can see how. Then end of life, it will either be 1.5 to 3 depending upon the road use. Is it a highway, urban, arterial, or is it residential? Then the load transfer coefficient J. This accounts for the load transfer efficiency, like essentially the lower J factor between the load transfer. So the J factor for the actual road test was estimated with 3.2. Typically the J factor values are as shown in the table on the next slide. Okay, so these are the J factors typically. As you can see here, if it's undoled PCC or crushed aggregate, if it's doled PCC, on a HMA without widening outside the lanes, it just depends on the scenario that you're designing for. Then we have the modulus of the subgrade. So the modulus of the subgrade, that's the K reaction, is used to estimate the support lag. So you use it to estimate how well can the subgrade support all the layers above it. So that's just the modulus of subgrade reaction. So now we'll move on to the outputs. Okay, so these are the outputs. Okay, so the outputs here, the outputs that you'd be expecting, I won't touch into all of that. We'll just go straight into it because it's kind of, I don't want to be repetitive. Okay, so you determine and gather the rigid pavement design. You determine and gather the rigid pavement SAL equation inputs. Then you determine the equivalent the equivalency factor for each load type. You determine the equivalency factor for each load type by solving the ESL equation using the assumed slab depth D. Then you estimate the traffic count for each load type for the entire design life and multiply by the calculated ESL to obtain the total number of EO expected over the design life of the pavement. Then after that, you insert the assumed slab depth into the design equation and calculate the total number of ESLs that the pavement will support over the design life. Then you compare the two ESALs from 5 and 6, and if they're reasonably close, say within 5% of each other, you use the assumed depth. If they are not, then you go back to step number 4 and you increase the depth of your pavement until they're within range. Then obviously the design utility. This design utility solves the 1993 ASSHTO guideline basic design equations for the rigid pavements. It also supplies some basic information on the variable description and typical values of the equation precautions, which is exactly what it does for the flexible pavement also. So yeah, I think we are done for this chapter. I will see you guys in the next chapter, which is chapter number 6. See you soon. Hi guys, welcome to chapter number 6. So we are only left with 3 more chapters. After this, we are almost there.